My name is Sarah Hessel, and I'm here today to talk about what is the best form of acetaminophen to take between the caplet, tablet, and capsule. So to figure this out, we want to determine the acetaminophen content and rate of release for each of those three forms. Unfortunately, acetaminophen is unable to be detected, so it has to be converted into ferroin so that the absorbance can be recorded. This is done in a two-step process where acetaminophen is oxidized with excess Fe3+ to convert it to Fe2+, which is then reacted with excess phenolphthalein to make ferroin, as shown in the diagram. So the experimental procedure, stock solution of acetaminophen was converted into ferroin using this two-step process shown, and then split into 5 different dilutions with varying concentrations. And the absorbances were then recorded for each dilution. Then each type of the acetaminophen, the caplet, capsule, and tablet, were then placed in 750 milliliters of hydrogen chloride and heated to 37 degrees Celsius. A sample of each solution was taken at every 2-minute interval for up to 30 minutes, and then converted into ferroin and diluted. And then the absorbances were then recorded. So to solve for the concentration of ferroin for the original dilutions, you take 1 milliliter of acetaminophen, convert it into liters, and then multiply by the concentration of acetaminophen to get the moles in that one acetaminophen in that 1 milliliter. Then, using the stoichiometry of the reaction, you can find the moles of Fe2+ in that 1 milliliter, and then dividing that by the volume, you can then find the molarity of ferroin. To find the concentration of ferroin for the dilution, use the dilution equation M1V1 equals M2V2 using the concentration of ferroin that you had just solved for to solve for the concentration after the dilution, as shown in the equation. Then you can use stoichiometry to find the concentration of acetaminophen of the dilution. Table 1 here shows the absorbances and concentrations of ferroin and acetaminophen for each of the dilutions. And figure 1 shows the standard curve for ferroin when you graph the absorbance versus the acetaminophen concentration. The equation for the line of best fit will then be used in the calculations later on. So after the table 2 shows you the data for the capsule, caplet, and tablet at the 2-minute intervals for the absorbances of each solution. And then it was then compared to the class average of each of those 3 samples. So the data from table 2 and 3 were then graphed, and they figured out that the leveling off point of the data points would show when the acetaminophen content had been completely released. These points were then averaged to find the average absorption of when the acetaminophen had been completely released. So for the figure 2, for the acetaminophen gel capsule, since there is no clear leveling off point, the last data point was used. For figure 3, every data point past 20 minutes was used as the leveling off point. For figure 4, for the acetaminophen time release of the tablet, the last 3 data points were used as the leveling off point, and for figure 5, it was the last 2. In figure 6, for the caplet, the last 4 data points were used as a leveling off point, and for the class average of the tablet, the last 3 data points were used. So as explained before, the leveling off points were then averaged to find the average absorption for all 3 forms, both class average and experimental. These are shown in table 4. So using the standard curve for ferroin and the equation of the line of best fit, the average absorbances can then be used to calculate the mass of acetaminophen that has been released. So replacing x and y in the line of best fit equation for the values of the x's, the average absorption can then be plugged in for the y and solve for the concentration. This is then multiplied by a diluting factor of 0.11 liters to solve for the moles of acetaminophen released. To convert that into milligrams as the theoretical units is multiplied by the total volume that it was, the 700 milliliters of HCl it was released into, and then using the molar mass of acetaminophen and converting it to milligrams, you get the experimental milligrams released. This is going to be used in comparison to the 500 milligrams theoretical for all three forms to find the percent error of each of the 6 samples. As shown in Table 5, all of the percent errors and the milligrams released of all 6 forms. So the next step in calculation was to figure out the rates of release of the tablet, caplet, and capsule for both class average and experimental data. This was done by graphing the data points for the 2-minute intervals, but leaving out the points that we consider to be leveling off for the acetaminophen being released. By eliminating those data points, we create a line of best fit of only the data points where acetaminophen is still being released. This makes the slope of the line of best fit between the data points the rate of release. So for figure 8, the rate of release of the capsule is shown to be 0.0419. For figure 9, the rate of release is shown to be 0.084. For figure 9, the experimental tablet data is shown to be the rate of release as 0.0469. And for the class average of the capsule, the rate of release is 0.0471, as shown in figure 11. In figure 12, for the caplet, the rate of release is 0.0674, and the rate of release for the class average tablet in figure 13 is 0.0427. Those rates of release that I just read to you are in the units absorption per minute, as per the axes of the graphs. These have to be converted to micromolar per minute using the standard curve of the Farrow equation and stoichiometry. So by plugging in what we have for the rate of release absorption per minute in the absorption column for y, we solve for the concentration. This will then be, this gives you the rate of release in concentration per minute, which is then converted into micromolar per minute. Figure 6 shows you the rates of release for the capsule, tablet, caplet, both experimental and class average. Now, as you probably realize, the experimental results were much higher than the theoretical 500 milligrams. This created a large percent error, and possible reasons for this could be that the solution fluctuated between the 37 degrees Celsius, not staying at a constant. Also, the 2-minute interval samples could not have been taken at exactly 2 minutes. This would have thrown off the data set and thrown off the data. Although there was a large percent error, there also was pretty much the same amount of percent error for the class average in comparison to our experimental. This shows that multiple lab groups made similar types of data errors. Before completing the lab, a hypothesis was made predicting the tablet to be the form with the fastest rate of release. This was disproven by both the experimental and class average data, which showed the caplet to be the fastest rate of release. This makes sense because the caplet does not have a protective layer of coating that has to be broken down in order to release the acetaminophen. It was important to use excess amounts of phenolphthalein because if not, it would have limited the reaction, causing not all of the acetaminophen to be converted into ferroin. By making Fe2 plus the limiting reaction, all of the acetaminophen is converted into all of the acetaminophen is converted into ferroin, making the data more accurate. However, if the reaction had not been heated long enough, it would not have gone to completion, making the acetaminophen contents lower than actual. For this presentation, I cited a published paper where I got the pictures from and my lab manual for Chem 160.